most complex and sophisticated machine ever made. In 6 minutes, it will be traveling at 17,500 miles an hour. In 8 minutes, the humans inside will no longer feel the pull of the Earth's gravity. When the 20th century started, humans couldn't even fly. As it ends, they're flying where no creature has ever flown, and they do it with rockets. Rockets aren't new. Neither is the idea of riding them to the heavens. One night in the 16th century, a Chinese nobleman, Wan Hu, prepared himself for liftoff. But then there was, as modern spacemen say, a glitch. And though Wan Hu didn't make it to the stars, he couldn't be found on the face of the Earth either. For 400 years more, spaceflight was confined to dreams and rockets to fireworks. But this century saw rockets take a deadly trajectory. It was alcohol, not gunpowder, that propelled Germany's infamous V-2s to London, but the principle was the same.
A rocket is essentially a high-tech version of a hot air balloon. A hot air balloon in the sense of a child's balloon. What a rocket does is have a barely contained explosion to generate high-pressure, high-temperature gas that's contained in a cavity. And that gas then squirts out at very high speed out a little hole, but it's still a barely contained explosion.
Sounds simple, but in their post-war rocketry, both Americans and Soviets found that containing the explosions was the tricky part. The US and the Soviets were caught up in a space race. Both wanted to be the first to put a human in orbit. And in 1961, the Soviet cosmonaut Yuri Gagarin became the first human to leave the planet. He had ridden into space on top of the powerful Vostok rocket, and he hadn't been blown to bits. The US reacted to the setback by concentrating on a new race. A race to the moon. They had the technology, the urgency, and the money. At the Kennedy Space Center, they built a vehicle assembly building, so large that a 45-story office building could fit through its doorway. The moon rockets would be carried from there to the launch tower on the world's largest land vehicle. Everything to do with moon rockets was colossal. The 360-foot-high engine test stand at Huntsville, Alabama, has more concrete in it than the Great Pyramid has stone. In 1960, when 5 Saturn engines were tested at the same time, the roar could be heard 100 miles away. All that power was needed. The ship that was going to be lifted off the planet, the Saturn V, was longer than a football field and weighed as much as 30 locomotives. The Soviets, of course, had blueprints for a moon rocket of their own. After all, the race was still on. But while the Americans were open about their space program, the Soviets were clandestine. But that just heightened the interest for C.P. Vick, amateur space detective. Vick had no connection with the U.S. government at all, and certainly no access to spy satellites. But that didn't stop him. He used images from Landsat, the NASA Earth Resources satellite, to find details of rockets that he could barely see. Using only material in the public domain, he became an international authority on the Soviet space program and drew the N-1 moon rocket long before the official drawings were released. And the drawings he made, which took weeks because of all the calculations he had to do, contained a lot of educated guesswork, but they were good enough.
My drawings were published in the Illustrated Encyclopedia of Space Technology in 1981. This was put on display in Moscow at a book fair, which many Russian rocket scientists visited. Subsequently, they ordered many copies of it. But at the time, they were saying in so many terms that I knew a little bit more than I needed to know. But ultimately, in recent years, we have actually been able to see what the launch vehicle looks like, as we can see over here. N-1 was a monster launch vehicle producing over 10 million pounds of thrust.
This is the first film ever shown publicly of the N-1 in flight. The Soviets planned to put a man on the moon a year before the 1969 U.S. Apollo landing. And here's the reason they didn't. They could never get all 30 of its first stage engines to work together. The N-1 may not have flown very well, but it was the biggest rocket ever to try to fly. It had 5 stages compared to Saturn's 3. But Saturn worked, and the N-1 didn't, because Saturn was simpler. Not that simple, though.
0. Ignition. Liftoff. Liftoff. 30 minutes after the
It takes a top speed of 25,000 miles an hour to fly to the moon. If you're in a hurry to make a rocket ship that will do that, the quickest way, though not the most economical, is to make one that burns in stages. Make 3 rocket ships. When the first one has used up its fuel, it simply drops off. That leaves the second one with a much lighter load to push. The spacecraft goes faster, and then the second stage drops away. Then the third engine fires, slings the ship around the Earth, and shoots it towards the moon. And so the age-old dream of humankind came true. But dreams that come true can often be followed by a feeling of anticlimax. Almost as soon as the astronauts were there, the media and politicians began to wonder if the trips had been worth all the money. And after 17 Apollo missions, the last of which wasn't even shown on television, the not quite finished rockets meant for the next series were just left lying on the ground. And then, in 1996, the National Aeronautics and Space Administration, worried that the rockets might rust away, decided to save one for history and put it in the Kennedy Center's Space Museum. Saturn is an awesome machine, and in the museum, a possible inspiration to future interplanetary travelers. But since it was last used in the early 70s, rocketry has been refined. Most rockets don't need to be nearly this huge anymore. Rockets are mainly business now. Slimmer, more cost-effective machines, built to carry useful, profitable satellites into stationary orbits. Orbits timed to move with the rotation of the Earth, so that the effect is to hang still in the sky. They've brought cellular phones, hundreds of channels of television, accurate weather reporting, mapping, navigation, space astronomy. All these things and dozens more have changed the world the satellites hover above. And much of the rocketry that puts the satellites there comes from the Lockheed Martin factory near Denver. It's one of the largest rocket factories in the world, making what are now the largest U.S. rockets, Titan 4Bs. These, along with the smaller Atlas and Centaur rockets, each hundreds of millions of dollars worth of precision equipment, are put together on an assembly line, just as if they were jet planes or Chevrolets. It takes about 3,000 people to make these rockets, but only about 200 are actually involved in their final assembly. Some of them working like surgeons in the so-called clean room. The upper stage Centaurs have to be clean because the satellites they carry really have to be clean. Any bit of dirt that lands on a lens or a mirror or in the inner workings will, in outer space, stay there for a satellite's lifetime, perhaps permanently impairing its performance. And this is the Titan, getting wired up. Titans are the workhorses of the U.S. rocket fleet, built to take the heaviest loads, up to 20 tons. Titan started life as a weapon, a ballistic missile. But its first space use was to launch humans, the Gemini missions, the preparation for the moon landing.
5, 4, 3, 2, 1, 0. Ignition. Liftoff.
Today it's commercial, and though it costs about $300 million to make, each launch brings millions in profit. And launching satellites, like any big business, is international.
9, 8, 7, 6, 5, 4, 3, 2, 1, stop.
The European rocket fleet, Ariane, launched from French Guiana, carries most of the world's biggest commercial payloads.
24, 23, 22, 21.
The Japanese have H-2 rockets. They have plans for moon orbiters, a space shuttle, and a space station.
全システム準備完了。
5、4、
メインエンジンスタート。 SRB 点火、リフトオフ。
The closer a launching pad is to the equator, the less power is needed to get the rocket up, which is why Ariane goes from Guyana and the H-2 is launched from one of Japan's most southerly islands. Subtropical Tanegashima, which makes it more fuel efficient than if it were launched from Tokyo. But what happens when a far northern country wants to get into the satellite business? Around the oil-rich North Sea, there are plenty of used drilling platforms. And now Norwegian, US, and Ukrainian companies have teamed up to convert a 31,000-ton platform into a launch pad to be towed to the equator. Rockets are assembled on the ship, transferred to the platform, winched up, pointed at the sky, and launched eastwards, parallel to the equator. The reason an equatorial launch saves fuel is that the planet turns fastest where it's the thickest, and the spinning speed of the globe there gives the rocket an extra boost. The rocket also has a shorter distance to reach geostationary orbit. In this orbit, 25,000 miles high, satellites travel around the Earth once every 24 hours. But when space stations are up and running, even cheaper rockets will be needed. Today's rockets are so expensive because they're used once and thrown away. Rockets regularly visiting space stations like this one will need to be reusable. And that was the original reason for building the space shuttle. Work on the shuttle started in 1972. It was supposed to ferry passengers and supplies into orbit, spend up to 3 weeks there, and then fly back to Earth like an airline. The shuttle's budget was tight, though, and didn't allow for all the necessary technology to be developed. And it was never entirely what it was meant to be, a simple, reusable spaceship. It now costs up to $500 million a launch. Even so, it's still a hell of a machine. And people who have seen a launch never forget it. To get all its 2,000 tons of dead weight off the ground, the shuttle relies on solid fuel packed inside the white boosters. Once high in the atmosphere, the huge external tank filled with liquid hydrogen takes over. The chief designer for this most intricate of machines is Max Faget.
Well, there's our shuttle. When it's all fueled up and ready to launch, it'll weigh almost 5 million pounds, which is a great deal more than we expected. The original idea was to have a vehicle that could carry astronauts up to the space station and back down, and perhaps a little bit of cargo. So it was designed to carry about 5,000 pounds, maybe a little bit more, with a crew of perhaps 6. However, as time went by, a lot more uses for the shuttle were invented, and it was decided that it should be able to carry as much as 60,000 pounds. And of course, that made the thing an awful lot bigger.
The shuttle is now the main source of human access to space. 10 or so are launched every year, each one carrying from 5 to 7 astronauts. 220 people, including 27 women, have been shuttled into orbit, and there have been 90 launches so far.
Main engine start. 3, 2, 1, 0.
Even so, this 1997 takeoff is the first that Max Faget, who worked at Houston Space Center, has ever seen in person. Riding upwards on a 600-foot trail of flame, the shuttle is a sight to behold.
Boy, that is bright. Super. That's the first time I've seen a launch since Al Shepard went to the moon. And it's just outstanding to listen to that noise. Of course, I've been watching them all on TV, which you can see a lot more, but to be here and see the thing live and hear that tremendous crackling roar of the launch, it's really been something else. And that's a great ship, I'll tell you. It doesn't meet everybody's requirements, but it's a super ship, and we're all proud of it.
The solid fuel boosters burn out in 2 minutes and are dropped into the sea, 160 miles from the launch pad. The shuttle is now powered only by the main engines. In 4 minutes, it empties the tank of 440,000 gallons. The tank will now break up. It's the only part of the operation that has to be wasted. As high as 370 miles up, the astronauts go to work. The shuttle crew can even pull up alongside satellites and repair them.
Sure did. About that. Are we in altitude?
Here, they're fitting eyeglasses on the faulty lenses of the Hubble telescope, a job that later helped astronomers see hundreds of things never seen before.
Final pre-clear maneuver of the
As amazing a vehicle as the shuttle is, there are elements of the 1972 jalopy about it. Its guidance computer, for instance, still uses cathode ray tubes, and the steel bearings in the oxygen turbo have to be replaced every second flight. Or did, until the shuttle engineers, along with the world of dentistry, caught up with some modern technology. A dentist drill operates under many of the same conditions as the bearings in the shuttle. They both have to withstand stresses at very high speeds. And in recent years, drills and bearings have both switched from steel to the much tougher ceramic, silicon nitride. Now the shuttle's bearings only need changing every 10 flights. Silicon nitride has saved the program millions. There are many other ways that new technology is improving the shuttle. In the main engine, for instance. No other engine in the world operates at such extremes or at such a range of temperatures, from freezing liquid hydrogen to burning gas. But that doesn't mean it can't be improved. Take the fuel injectors. They determine how well the fuel mixes with the oxygen. The better the mix, the more efficient the engine. This is an optical patternator, which uses lasers to look for possible improvements. It's a tribute to the shuttle's basic design that it can be updated a piece at a time. What will finally outdate it, though, are these. The next generation of lighter and more powerful space planes. Planes such as Hope of Japan. It will ride into orbit on top of an H-2 rocket, the kind now used for carrying satellites. Hope is a speedboat to the shuttle's cruise liner. It's a compact ship, built to take 2 or 3 astronauts to and from an international space station. And when it lands, it's entirely intact and as ready as it'll ever be to go up again. But for a whole new approach to landing, not to mention takeoff, there's Clipper Graham. Built in the U.S. by McDonnell Douglas, it's the kind of rocket ship Buck Rogers would have used, and it's the first completely self-contained spacecraft ever made. In this Air Force test flight at White Sands, New Mexico, it demonstrates a talent never before seen in a rocket. It can go up into the sky and just stop. Just hover there. It can tilt and fly laterally. And when it's ready, it can reverse straight back down to the launching pad.
We're on the way down. Engines coming up to slow the vehicle.
Landing gear limit.
We're now descending at 110 feet per second.
Rather, it could do this, because Clipper Graham is no more.
Landing
Engines
accelerated.
coming up to slow the vehicle further.
Landing small negative. Gear down.
Gear is down, descending toward touchdown.
Way on gear, engine shutdown.
This was only an experimental prototype. After 4 successful flights, it crashed and burned. Maybe it knew something. Maybe that the contract for the next U.S. space plane had been given to Lockheed Martin and the X-33. This will replace the shuttle. And many of its best features are the result of lessons learned from the shuttle. Take its heat shield. The shuttle's is notorious, stuck on ceramic tiles with a tendency to fall off.
These tiles are great thermal insulators, but they're fairly fragile and require a considerable amount of maintenance between flights. Estimates are that it takes between 17,000 and 70,000 hours between flights to maintain the thermal protection system. For the reusable launch vehicle, we'd like to do a lot better than that and be able to support a 7-day turnaround between flights. We're looking at metallic thermal protection system panels such as these, which consist of a stiff outer metallic shell which surrounds lightweight fibrous insulation made of aluminum. These panels are bolted onto the vehicle structure rather than glued on as the shuttle tiles are.
Even when testing models in wind tunnels, there are new technologies undreamt of when the shuttle was being developed.
Phosphorothermography is a method where we coat ceramic wind tunnel models with fluorescent crystals, such as this one here. We illuminate the model with ultraviolet lamp during a wind tunnel run, and the model then glows with an intensity which is temperature dependent.
Looks like we're ready to run when y'all are. We don't need a calibration or anything, and it'll be a 250, 450, and we're giving you permissions.
So, just by looking at the colors, the scientists can tell how the X-33 will be affected by the re-entry heat. But for absolute precision, the wind tunnel information is transferred to computer. Other design components are being tested. This stress test simulates the extreme temperatures from launch to re-entry landing on part of the X-33's lightweight reusable fuel tank, which must withstand temperatures that range from 350 degrees to minus 420 degrees. And then there's the stress of going to space. A titanium sandwich joint? Where is the breaking point? When will it surrender to the pressure? Under this tension, metals can be ripped apart with a deafening bang. This time, the battle between the test machine itself and the joint was a draw. The X-33 will have a special engine, the Aerospike, which automatically adapts to give the best possible performance at every speed and altitude. And so it has to be tested at every speed and altitude. At least every speed and altitude that a Blackbird spyplane can reach. The X-33 is scheduled to launch in 1999. It will be distinctive for having no wings, or being all-wing, a flying wing. And though it will weigh half as much as the shuttle, it will carry the same weight. Even better, it will be completely reusable. It will make spaceflight routine. It will be able to do what the shuttle was originally intended to do. Service space stations. And service more than space stations, maybe. Because when space travel becomes so easy and relatively cheap, there's no reason why it should be limited to professional astronauts. How about a honeymoon in a space hotel?
The height of this hotel will be about 240 meters, and the diameter is 140 meters. And this is rotating 3 times a minute. And we produce artificial gravity that is 0.7 G. The size of guest rooms length is about 7.5 meters, and the diameter is about 4 meters. So very, very comfortable because we have a gravity of 0.7 G. We have 64 guests we can invite for this hotel. But the most interesting portion is this zero gravity area. So we can enjoy the zero gravity sports, games, and also drinking and eating, very much different from the drinking and eating on the Earth.
Oh no! Relax, relax! Zero gravity has no effect on capillary action, you know.
All you need for this kind of future is cheap rocketry. Or maybe not rocketry at all.
The space launch systems of the future are not going to be rockets. These machines are going to be incredibly energetic. They're going to be so powerful that you'll be able to idle to orbit in such a machine. The rocket is a remarkable achievement, and we've accomplished many wonderful things with it. But you have to realize that the rocket has to carry all of its propellant on board in huge, massive fuel tanks. It's very much, to me, like sitting in the back of a boat trying to propel it by chucking cannonballs out the back end. Imagine the opportunity of designing a vehicle to fly on remote power beamed to the vehicle, a light craft.
The light craft. It's a completely different approach to space travel, or any kind of travel for that matter. A laser is driving this. When the high-energy light hits the back of the mirrored circle, the air behind it gets so hot it explodes and shoots the light craft forward. White Sands Missile Range. Mirabeau and his team work here, trying to create a system that could make rockets obsolete. And using some of the world's most powerful lasers, leftovers from President Reagan's Star Wars program, which was based here. These beams of concentrated light can travel hundreds of thousands of miles without losing any focus, and Mirabeau believes that they could drive a ship into outer space.
We're now preparing for an actual free-flight experimental launch of a laser-boosted light craft. We've set the model here on a short wire launcher, and we have to spin the model like a child's top or gyroscope so that it will automatically point at the laser beam during boost. So now we'll spin this up right before launch.
Laser on, air explodes, and the model rises to the stars, or in this case, the ceiling. The landing is tricky, too. After all, this model is worth about $4,000 and is easily damaged. With his models, Mirabeau is gradually increasing both the scale and the detail. Within 5 years, he hopes to lift mini-satellites to orbit with a craft such as this.
This is a full-scale model of a laser-propelled light craft. The entire vehicle is as you see it here. There are no external tanks. There's a small propellant tank inside. The front end of this is where the satellite electronics go. The whole front end of this thing becomes an inlet to make this engine supplied with air on the way to orbit. The back side of this is a large parabolic mirror, highly polished, that is designed to capture the laser beam that is projected to it from the ground onto this optic, and it focuses the laser power right inside this shroud here. When that happens, an explosion occurs as the air is rapidly heated, creating a shock wave that pushes this vehicle forward. As the beam is rapidly pulsed, the engine is continuously propelled on its way to orbit. Why should astronauts have all the fun? I mean, I want to go to space. I can't afford it. It's too expensive. I could afford it if it was for the price of an airline ticket. And that's why I'm developing lightcraft technology, because it would open up space to everyone.
There's even a second generation of ideas about beam-powered spacecraft. Close to the Earth, the craft converts sunlight into electron beams that spin like a fan, moving it in any direction. Then it flips over. An orbiting solar power station hits it with a laser or microwave blast to generate 9 billion watts of electricity. This powers a remarkable engine that forces air downwards and even pushes the atmosphere out of its path. The 60-foot craft and a dozen passengers could reach the moon in just 5.5 hours. a solar-powered, virtually free ride. Outer space, by its nature, offers other opportunities for free rides.
Houston, we have satellite motion.
All right, we see it.
In orbit, for instance, a simple piece of string gains all sorts of potential. This experiment aboard the shuttle, where a satellite is being dropped into orbit, could be a step towards launching systems that work like slingshots. This attic in San Diego, California, with its futuristic spinning wheel, belongs to Joe Carroll, a man with plans for tethers in space. One of the critical jobs in the tether business is winding the reel. The string, made of high-strength polyethylene, is miles long and must deploy freely.
This is a prototype test winding with a new type of tether that is strong enough to actually tie the space shuttle to the International Space Station after it's built. And then at the end of any shuttle mission to the space station, whatever surplus propellant is left over can be used to reboost the space station in a towing mode. This tether is about 3 kilometers long. It'll take about an hour and a half to 2 hours to wind. For the 20-kilometer tethers, the actual winding time is about 8 hours. That's distributed over a longer period with, lunch breaks and things like that. I've been a space enthusiast for 30 years and never expected my concepts that I played with as ideas to be taken seriously. But 15 years ago, NASA got interested in a concept of mine involving a way to use tethers. This led to my opportunity to build flight hardware, and it's been a great satisfaction and very thrilling to have the opportunity to fly your own hardware and actually see it in space.
Launched by a rocket in 1994, this satellite tether was the first man-made object in space to be visible from Earth as anything but a point of light. It had a shape.
This experiment was satisfying and exhilarating in many respects, but one of the most surprising was the fact that the tether itself was actually visible to the naked eye. It was a great surprise to many people that something about the size of a kite string would be visible from hundreds of miles away.
You calibrate your scopes with it, get some resolution.
Some people described it as a glowing Jedi sword gliding across the desert sky.
Joe's remarkable 12-mile-long tether was visible to the naked eye because it was shiny enough to reflect sunlight.
Oh, this is great. What? It's great through the binoculars.
Soon tethers may move cargo, maybe even manned spacecraft, from Earth orbit to the surface of the Moon. It's all a matter of energy transfer. When there's no atmosphere to interfere with an object's momentum, momentum can be passed from object to object. The cargo is grabbed by the tether system, then maneuvered through space to higher orbits. To get to the Moon, it's a 4-day trip. In lunar orbit, the parcel is caught by another tether and dropped gently down to the surface of the Moon. And of course, it would work just as well in the opposite direction, which means that there could be constant traffic between Earth and Moon without the cost of fuel. But the Moon is just a local stop, and space, to say the least, is vast. What about going to the nearest star, Alpha Centauri, 100 billion moon distances away? Even the difference between the Moon and Mars is like the difference between the house next door and one in another city. So to travel in deep space, other technologies will be needed. Here at the Air Force Research Laboratory in the sunny Mojave Desert, they're working on solar propulsion. The pressure of sunlight on solar panels could push ships through space, or the light could be converted into power for electric motors. Or an inflatable solar concentrator like this could heat the propellant in rocket engines. This would allow for rocketry, but with much lighter fuel and much more efficiency. Nearby, a new type of fuel is tested in chambers that simulate space. This is a pulsed plasma thruster. It heats Teflon to a temperature so high that it turns into a completely different state of matter, a plasma. This can maneuver spacecraft or satellites. But how do you invent a new rocket ship? To do that, there's a remarkable computing system that seems to turn dreams into reality. It's called rapid prototyping. A designer draws into a computer, and then another computer takes the drawings, analyzes them, and compiles them, layer by layer, into the designer's wish. This means that anything a designer can draw, the computer can make. A laser traces the designer's thoughts into a bath of liquid epoxy resin. Wherever the liquid is touched by the beam, it solidifies. Little by little, one thin cross-section at a time, three-dimensional parts are formed. And in a matter of hours, the finished object rises out of a solution bath. You can make almost anything you need with this. Spare parts on long space missions, for instance.
NASA's involved in rapid prototyping not just to reduce the cost for models used in wind tunnel or hot fire testing, but we're also involved in research to develop machines, perhaps one like this, to support the astronauts on the space station or during the exploration of other planets.
Rapid prototypers could be crucial on missions to Mars. A space dock could be the launch pad for a ship that could get there. When its engine's running, a nuclear rocket ship is highly radioactive. On Earth, this is dangerous, but space is full of radiation already, and a little extra from the ship would be like pouring a glass of water into the ocean. A nuclear engine, essentially a nuclear reactor, could drive a rocket twice as fast as a chemical engine and provide a safer ride, too.
To get to Mars and back, using current technology such as the chemical rocket engines on the space shuttle, will require 3 years. The reason for this is that it'll take you 6 months to get to Mars. If you spend a month or two exploring the planet and then try to race back and catch to the Earth, it is revolved around the sun. With a nuclear rocket, we can get to Mars in 3 months. Then we can spend a month or two in exploration, and then we can achieve speeds of up to 30,000 miles per hour, racing back and catching the Earth before it gets too far around the sun. Thus, the total mission time, round trip, is about 9 months. And from the crew standpoint, being out in space, cut off from the Earth for only 9 months, is far, far safer than a 3-year mission. So in my opinion, nuclear propulsion is an enabling technology. I believe that within 10 years we can design, build, and test a nuclear rocket that will allow us to launch a manned mission to Mars. For any manned mission that goes beyond the moon, faster is better. On a 3-year mission, the crew would be exposed to a radiation dose that exceeds their allowable lifetime limit. Because of the performance of the nuclear rocket, not only can we reduce the trip time, we can actually put shielding around the module in the ship on the journey between Earth and Mars.
That's all right for Mars, then. But what propulsion system could be used to reach the stars? For starships, it's antimatter. This, the equal and opposite of matter, can be made in enormous atomic accelerators by smashing normal atoms together.
I first became interested in space travel about 10 years ago. I had, before that, been doing experimental particle nuclear physics, thinking at odd moments about how we could use the results of that research to make spacecraft fly. The challenge for the next generation of rockets is to go into deep space. That is, to explore the outer planets, let's say starting with Mars, and then to go into interstellar travel. Chemical rockets simply do not contain enough energy per pound of fuel to enable those missions.
The amount of antimatter in a matchbox could replace a boxcar of traditional nuclear fuels for powering spacecraft of the distant future. But until recently, there wasn't any way of taking antimatter to your rocket.
It's a prototype instrument which we are just completing. It's designed to trap and hold 10 billion antiprotons for a period of up to 10 days. Our plans are to manufacture a much more substantial trap, but will handle up to 1,000 billion antiprotons. That number is significant and will allow us to trigger microfusion reactions with the antiprotons. And in turn, that would enable robust space missions. We're talking about very fast missions to Mars with a very substantial spacecraft delivering perhaps 100 metric tons to the surface of Mars with several astronauts in a very quick period of time, round trip 120 days.
So antimatter suspended by magnetic and electric forces in supercooled thermos bottles could be the fuel for massive space liners. Once a second, the antimatter would detonate an explosion like a tiny hydrogen bomb. For now, though, the only crafts using antimatter are those belonging to the Star Trek fleet. And even they have their limitations.
By my calculations, we're going to need 50 years to get to Alpha Centauri using nuclear power, and that will be even a great challenge. So if we want to bring the people back, that would be 100 years round trip, and that exceeds the lifespan of most people that I've known in my lifetime. On the other hand, if we want to leave them out there, why, that's something to think about.
Antimatter really offers pretty much the only option to do an Alpha Centauri type mission in the time frame of interest. You always have to trade distance and time. It's really a speed question. And then if you have more massive ship, it takes more energy to get your ship up to that speed. So antimatter, in my opinion, is the only thing that offers the potential, unless you're willing to invoke some kind of new physics.
Our universe has evolved over a long period of time, and there are mechanisms and forces that are responsible for that evolution. And the more we travel in space and look at these objects, admittedly far away, and study them, the more we'll know about our evolution and our origins. And that's why I'm an enthusiast for space exploration.
One whose ideas may seem a little primitive to us today. There were so many things they didn't realize.